What we're going to be doing today is looking at using matrices and inverse, or specifically inverse matrices, to solve systems of equations. Now, if I took a matrix, or a system of equations, let's just look at a general system of equations. This here isn't in your notes. And we had cx plus dy. Well, if I'm just looking at this here, I'm going to define it as ABCD times x, y. I'm able to rewrite this part here as ABCD times x, y. Well, let's actually look at the multiplication and see why this works. Because when we multiply two matrices together, well, this here is a 2 by 2, and this here is a 2 by 1. So the columns of the first matches the rows of the second, which says I can multiply it. And what I'm going to finish with is what? A 2 by 1, yes? So let's multiply. So I would go over and down. So I'd have a times x plus what? B times y. Isn't that what I had at the start? AX plus BY. Let's do the other one. Over and down. C times x plus D times y. Don't I get back to the same thing? So I can rewrite systems of equations as this form here. And really, whatever this is equal to, say 9 and 7, well, I can set this equal to what it's equal to as well, because it'll work out to be the same thing. And what it works out with these here is, again, just kind of as I set up here, we can rewrite this using the coefficients times our variables and set it equal to what it's equal to, kind of what each equation is equal to. We'll call it the constant matrix. And we have this here. Now, in a more general sense, what this is saying is that I have matrix A times our xy is equal to matrix B, our solution. Yes? Now, if I multiply by an inverse, if I multiply by A inverse, what do we know about A inverse times A? A matrix times its inverse. What do we get? If they are inverses. It wouldn't be 0. It would be our what? Because the only way that we know that two matrices are inverses of each other is if their product is what? There's a certain number, a certain setup.
0 or 1, 0, and then 2.
Which we called the identity matrix. Because if I end up with the identity matrix, then they are inverses, yes? And we saw that the identity matrix times anything just gave us whatever that was. So really, when I multiply this by the identity matrix, what I'm left with would just be xy. Yes? Now, when I multiply this other side, I would, there we go. When I multiply B by the inverse, because what I do to one side I have to do to the other, does it matter which side I multiply it by? So I could do this here. Yes? Well, matrix B here is a 2 by 1, yes? A is a 2 by 2. So I can't do it that way. So if I'm going to multiply by matrix A inverse, I have to do it from the left. Well, looking at this here, which side did I multiply A by? I multiplied it on the left. On the other side, I have to multiply it on the left. Because again, with matrix multiplication, order matters. The order in which we multiply does matter, because if we're multiplying it from the left or the right. order does matter. A inverse. So X, the value is going to be A inverse times B, whatever that is. Whatever that product is will be our solution. So let's actually look at a problem. This is going to make more sense when we look at it. So when we look at this here, so we're going to solve this system using matrices. Now the way we set this up is we're going to have a matrix times xy is equal to our matrix. Now the numbers that go in front here are our coefficients, so we would have 2, 6. Now one of the things I would make sure to look out for is to make sure all the x's, all the y's, everything lines up. Just like we did before, we need to make sure everything lines up, x, y, z. Now over here is going to be what it's equal to, so the top one was 18 and 0. Now at this point here, we went over how to find an inverse yesterday. As we talked about how we find an inverse yesterday, because for a matrix A, yep, nope, Zach, heads up. Almost, I'll get it. For a matrix A, it's going to be 1 over the determinant times our kind of rearranged matrix. And we talked about that kind of yesterday. This setup here. And we could do it that way. Or, what we can do is something a little bit different. Now, some of you actually did the inverse in the calculator yesterday, and I'm going to walk through it here. I didn't actually show you how to do an inverse yesterday. Now, the way we're going to go about doing this is I'm going to go second. Oh, these buttons are smaller. Second matrix. And we're going to go over to edit, and I'm going to edit matrix A. Which is going to be a 2 by 2. So our matrix A that I'm looking at is at -7, 2, 6, and 6, because that's what I want to take the inverse of. So I'd have our -7, 2, 6, and 6. And this is what we're going to take the inverse of. Because really what we're looking at is here, I've set this up as matrix A. Yes? In the calculator, this is matrix A. Now what we can also do is set this one here up as matrix B, this 18, 0. So in the calculator here, at this point, we can go second quit, second matrix, over to edit and go down to matrix B, and it's going to be a 2 by 1, and we're going to have 18, 0. Second quit. Okay. So we've done that, yes. Do I need to put the other matrix into the calculator? Well, no, it's just x, y. Those are our variables. So let's look at this here. So we said that I have matrix A and the matrix x, y is equal to matrix B. Well, if I take this here and multiply it by A inverse, on both sides. Well, A inverse times A simplifies to the identity, which is 1, which would be a multiplication of 1 for matrices, which will just really leave us with xy is equal to. Well, over here I still have A inverse times B, yes? Well, we already know what matrix B is, correct? Because that's our 18, 0. I don't really know what A inverse is. So we could do it by hand, or if I get the calculator, we can call up matrix A. Second matrix, enter. So I've called it matrix A, yes? And I talked about the inverse button yesterday. That x to the negative 1, it's right above the x squared. And if I hit enter on this here, it tells me this is its inverse. If I want to, I can go math, enter, enter, and it'll tell me this is the inverse as fractions. Yes? Is that what I really wanted to know? Did I really want to know what the inverse was? No, I wanted to know what the inverse, A inverse times matrix B. Yes? Okay, I'm going to do this again. Let's go clear. Oh yeah, that's right. Second matrix, A inverse, right? Because we're taking that A inverse times what? Times second matrix B. Because that's what we're talking about for this here, because this product, A inverse times matrix B, as we set it up, will be the solution, which is negative 2 and 2. Negative 2 and 2. So if I come back over to these slides here, so this product here gave us negative 2 and 2. So as a coordinate point, the x value would be what? And the y would be 2, because it's saying x is equal to negative 2, y is equal to 2. Because when we're solving systems of equations, we're looking for the point of intersection.
I was ready for you to see. I was going to plug it into a graph if I just
No, it's really, whenever we solve systems of equations dealing with x, y, we're looking for the point or line that they intersect or cross. It just for two variables, we're looking for a point. So that's it. Questions on this here? Any questions on any of this here so far? Okay, let's look at the next one. So for this one here, we're going to do the exact same thing. We're going to do the exact same thing. So what I could do is I could set the matrix E up as our matrix times xy is equal to our other matrix. Now the coefficients in the first, well, if I look here, x and y are both lined up already, so we're good. X is first, y is second. So we'll have 7, 2, negative 1, 2. Negative 19 and 21. So we have this here. So we're just plugging these in. So the 7, 2, negative 1, 2 are just the coefficients, numbers in front of the variables. Our variables, and then we set it to what it's equal to. At this point here, we can use the graphing calculator to plug these in. So at this point here, we can go second matrix over to edit and hit enter. Now for this here, are we still dealing with the 2 by 2?
Yes.
Yeah, so enter. So this time we have 7, 2, -1, and 2. And we can go second, quit, second, matrix. And we can go down to matrix B, which is still going to be a 2 by 1. But this time it's going to be -19 and 21. Huh? Okay. And now at this point here, we can go second, quit. So I'm going to look back over at the slides here. So as we work this through, really, I'm just going to rewrite it as A times our xy is equal to our matrix B. Well, what are we going to do to both sides? We're going to multiply both sides from the left by A inverse. Because A inverse times matrix A is the matrix version of 1. When we multiply those together, we get the matrix version of 1, which is just the identity matrix, which leaves us with xy. Now on the other side, we're just taking A inverse times B, yes? Now, at this point here, you're probably thinking, because, again, your calculator probably looks just like mine here, yes? Because have you been following along? Okay, now I would need to go and do second matrix A, then do the inverse times second matrix B, yes? Yeah, let's do 3 steps. If I go up, 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 well, too far, down one. If I go up twice, I have that selected. I have it highlighted, yes? It won't look the exact same as this here because this is in color. Yours is not. Hit enter. It brings it down, yes? If I redefine A and B for this new one here, yeah, we went through and redefined it for new numbers. So if I go up selected and bring it back down, it'll put the new numbers in. So our answer for this here is -5, 8. So once we type it in once and we change what A and B are for our new situation, it will change it for us. All we have to do is recall it. But we have to be careful in making sure that we fix both correctly. And what I mean by that is if I only changed A, I didn't change B for this problem, it still had the 18,0 from the last one, it would give me the wrong answer because it still thinks B is that 18,0. Does that make sense? So this here, recalling it is a handy tool, but we need to make sure that what's going in for A and B are correct. Matrix A and B are correct. So -5, 8, or we get it as the point -5, 8. Any questions on this here? Any questions on any of this here? Do we need to see another example of one of these? We good with these here? Yeah, let's look at this one here. So I'm going to go on and just plug everything in. We get this here. So again, we got the numbers in front in the first matrices from the coefficients, the numbers in front of the variables. So we got 4, negative 1, negative 2 as our first matrix. Then we multiply it by xy and set it equal to the matrix 20, 10, or 2 by 1. And those two numbers come from what it is being set equal to. Any questions on this here so far? Okay. Now we could do this by hand or we can do this in the calculator. It doesn't matter which one we do. Let's just continue on doing this in the calculator. So I'll pull the calculator up and I'm going to put both of those matrices in. So we go second matrix and over and edit matrix A, which is our 2 by 2. And this one here is going to be 4, negative 1, negative 2, and negative 2. So we input matrix A in. Then we go second quit, second matrix. Yep. I didn't hit second. And go over and down, edit matrix B, which is still a 2 by 1. And this here, this time will be 20 and 10. And once we get that plugged in, we can do second quit. So what do I know that I'm going to end up doing? Is I'm going to multiply that matrix A inverse by matrix B to get the solution. Yes.
Could you increase it by like 3 by 3, 3 by 3?
Yes. So we need a new page. Let's see here. So it's not going to give us one here. Well, I just need to find one. Because I would try to make one up off the top of my head, but doing that, well, getting it to be a nice system of equation is hard to do. I think I've done it before, but I'm not going to roll those dice today. Okay. So what we'll do next is we'll look at this 3-variable system of equation. Now we'll do it the exact same way. So going across the top, we'll have 4, negative 2, 7. The next one's going to be 5, 3, negative 5, and then we'll have negative 7, negative 8, negative 5. And this time it's not multiplied by xy, it's going to be what? X equal to 26, negative 50, and 55. Because when we look at this here, well, we just took the coefficients to make a 3 by 3 instead of a 2 by 2. Instead of xy, we have xyz, and here we have 3 numbers. So it's almost the exact same thing, it's just we have more numbers this time. Okay. Now, when we look at the calculator this time, so this time we'll do second matrix still. I'm going to go over and edit matrix A. But this time I have a 3 by 3, 3 rows, 3 columns, 3 variables. So we're going to do 4, 2, 7, 5, let's see here. No. Apparently I didn't get 5, 3, negative 5. So we got the first matrix in. Now we can do second quit, second matrix, and go over and edit matrix B, which is now a 3 by 1, which gives us a and we'll end up doing the same thing.
Well, if it's turned into fractions, it's negative 115 over 43, like 285.
No, there's an error somewhere else. Did I feel like I combined two problems when I did this?
A was correct. I typed in C was correct. I changed the matrix.
Ah, I see it. So this is the process that we would do to get this. But if you really wanted to get whole number answers, that should be negative 3 and that should be 49. But even though we didn't get whole number answers, the process that we did for this remains the same. It remains the same. Now, we're not going to get any cases, on this homework assignment, we wouldn't get any all real solutions. And if we're dealing with all real solutions, it's going to be easier to use our RDF, our reduced row epsilon form. And if you remember that, that took us down and gave us a matrix like this here, if you remember, 3 by 3s or 2 by 2s. Well, this part here is just the identity matrix kind of deal. So these here are a little bit easier to work with, especially if we're trying to see if it's all real or no solutions. Because if you remember with these here, because that was a solution. This here was our all real solutions because we had a row of all zeros. Now we knew it was a no solution when I had this here, because essentially that was saying 0 is equal to 1, which doesn't work. So this here, this reduced row epsilon form is easier to work with, especially if we're trying to navigate between all real and no solution. But here we're not going to have all real case. So if it doesn't work out, it's no solution. But that's it.